So welcome back. We'll be discussing the filtration aspect of water treatment in this video. Now, in this video, we'll talk about comparison of slow sand filter and rapid sand filter. So as we know, filtration rate is one of the major important items for rapid sand filter and slow sand filter. So 100 to 200 liter per hour per meter square for slow sand filter and 3000 to 6000 liter per hour per meter square for rapid sand filter. Filter sand size finer for slow sand filter, coarser for rapid sand filter. Base gravel 30 to 75 centimeter depth. Usually we'll put around 50 to 60 centimeters in between, whereas for rapid sand filter 45 to 60 centimeter depth. Method of cleaning, if you look at the top 15 to 30 mm sand bed is scrapped during cleaning, and backwashing is done with compressed air for rapid sand filter. Period of cleaning is around 1 to 2 months for slow sand filter, and rapid sand filter 1 to 2 days, but usually 24 hours operation is carried out. Coagulation is not preferred because of the small size of the particles before SSF, but it can be applied before rapid sand filter. Because of the low filtration rate, the area required will be very large in slow sand filter, and relatively is a smaller area in the rapid sand filter. Skilled supervision is not required, just allowing the water. Only cleaning is very simple operation. Whereas the rapid sand filter, the number of valves to be opened and closed during cleaning and backwashing operations. So it requires a skilled operation. Depth of the sand, 105 centimeters, 60 to 75 centimeters. And what is the wastewater or wash water? We normally go for 2 to 5% of filtered water. Here, the backwash is also done with the backwash water, but very small amount of small amount of water is used to avoid air trapping and slight expansion of the bed. Efficiency, you can look at the bacterial removal efficiency is up to 99%. A small amount of color and turbidity is removed. And whereas rapid sand filter, they are good in removal of turbidity and color, but bacterial efficiency is slightly less. High initial cost for slow sand filter and moderate affordable in the slow sand filter, because high initial cost means because large area requirements. And turbidity is another criteria in these operations. So if you look at the pressure filter, this is a compact filter. Compact filter, because of the high amount of filtration rate, the area requirement is very, very small. The requirement, the filtration rate is 6,000 to 15,000 liter per hour per meter square, and is applied at a pressure of 3 to 7 kg per centimeter square. So you can have, this is a vertical section, or it can also be a horizontal cross section here. So it occupies less area and treats higher water load per unit area. Advantages where water is received under pressure, and the diameter of the vertical varies from 2 to 2.5 meters, and length varies from 2.5 to 8 meters. The coagulated water is directly applied to the filter without mixing, flocculation or conditioning. Sand bed is 50 to 60 centimeter, while backwashing is used to clean the filter. You can see here, this is sand bed, and then bed support gravel is there, and on top of which you're having water. So usually they are provided with the inlet here. The water will come through the inlet, falls on the sand bed, support is there. Now at the bottom you see strainers are there, and from the strainers you're having an outlet pipe. Through the strainers, water is collected through the outlet at the bottom. This is nothing but under drain system. These are the inspection holes. We can look at what type of process is going on, whether water is standing there or not, any leakages are there, all such type of things you can understand. A number of options are possible here. right? So this is all about the compact pressure filter. So what are the way you are going to apply? These are not applied for the regular um, customer use for city population and town population, but they'll use it where their industries, particularly in swimming pool, where water is recirculated, we are going to make use of this. So their another drawback is they're unreliable to remove the bacteria, and hence they are not used for municipal water treatment. So let us look at some small examples to understand the calculation part. Design a rapid sand filter and slow sand filter for a raw water flow of 5 mld. Assume suitable data. The first and foremost thing is we have to assume the filtration rate. 3000 to 6000 liter per hour per meter square for rapid sand filter. So we assume some value here, 5000 liter per hour, and the 5 mld means 5 into 10 to the power of 6 liters per day. Per day means 24 hours. And surface area, filtration rate, always you have to remember, is filtration rate is equal to total discharge divided by area, surface area. So you want to calculate area, so you take this side and bring filtration rate to the denominator. That's what we are trying to do here. 5 into 10 to the power of 6 liters divided by 5000 liter per hour. So that's why we are converting per day to hours, 24 hours, 42 meters square. But for rapid sand filter, the maximum limit is around 50 meters square. It should not be more than that for practical considerations. So we need not have to divide into number of components. So here, when you assume LYB is equal to 1.25 in the range of 1.25 to 1.35, and substituting, you are getting B is equal to 5.8 meters and L is equal to 7.25 meters. And usually we keep one more filter for standby, the operational point of view. For slow sand filter, here also we have to assume the uh, desired filtration rate within the range of 100 to 200 liter per hour per meter square. So I'm assuming here 200 liter per hour per meter square, and subsequently I'm calculating, and what I got is 1041 meter square. The maximum area permitted is only 1000. So that's why what we should do is we should divide into two beds. So we're having 1041 divided by 2. So each filter bed of a slow sand filter should not be more than 520 meters square. So if you adopt the same ratio of L 1 is to 2.5 L by B and calculating here, so B is equal to 20.4 and L is equal to 25.5. So for construction point of view, we just round it off to 21 meters width and 26 meters length, and there should be two numbers. So what another problem, a rapid sand filter is having 10 numbers of 4 by 6 meter beds provided to treat 10 mld of raw water. Calculate filtration rate. If two beds are not functioning, what will be its filtration rate? First of all, what we have to look at is how much is the water to be filtered. This is given as 10 mld, 10 mld raw water, 10 million liters. That is 10 into 10 to the power of 6 liters per day. This first of all, you should write this. Then the surface area is given as 4 to 6 meters. So that is 240, 24 meters square. How many beds are there? 10 beds. So 10 into 4 into 6, 240 meters square. So now this should be converted into filtration rate. Filtration rate is equal to discharge by surface area. So if you write this, this is liters per day per meter square. But usually we express in terms of liter per hour per meter square. So therefore, you divide by 24 to get 1736 liter per hour per meter square. Now the second part, if two beds are not functioning, number of beds will be equal to 8. So accordingly, the area of the filter beds is 8 into 4 into 6, 192 square meters, 192 square meters. The amount of filtered water is not changing. So accordingly, when you are recalculating, it is around 2170 liter per hour per meter square. And this is another problem. A filter unit of size 4.5 meters by 9 meters is handling 10,000 meter cube per day of water in 24 hours, right? The filter is backwash at the rate of 10 liter per meter square per second for 15 minutes. Calculate or compute average filtration rate, quantity and percentage of treated water, and the rate of wash water flow in each trough if 4 troughs are provided. First of all, always we should write the discharge. How much is this? 10,000 is nothing but 10 into 10 to the power of 6 liters per day. Our size of the bed, 4.5 into 9. So 40.5 meters square. So filtration rate is always discharge by surface area. So this is a discharge by surface area will give you liters per day per meter square. The convention is to have liters per hour per meter square. So divided by 24, how much we got? 10,300 liter per hour per meter square. So first problem is solved. Second one is quantity of wastewater used for washing. How much is the time? 15 minutes. What is the rate? 10 liter per meter square per second. 15 minutes means this is given in terms of seconds. This is given in minutes. So convert this into seconds. 15 into 60 is the number of seconds. 10 liter per meter square. Per meter square means water. Again, we have to calculate the area and put here. So 10 multiplied by area, 40.5, and 15 into 60, you're converting time into seconds, and that is coming out to be 364,500 liters, or you convert this into meter cube, it is equal to 364.5 meter cube. So now what is the percentage? This volume of water divided by initial volume. Initial volume is 10,000. The wash water volume is 364. And accordingly, you calculate the percentage, you are going to get 3.645 percentage. And what is the last one? 4 troughs are provided, right? That is what we have to understand. The 4 troughs are provided. This wash water is now flowing through this 4 troughs. Wash water is flowing at the rate of 10 liter per meter square per second. So 10 liter per meter square per second. So here 10 liters multiplied by meter square area of the bed 40.5 is going to give you 405 liters per second. 405 liters per second is the total wash water used, and how many beds, how many troughs are used? 4. So divided by 4, 101.4125 liters per second. This type of the problems are generally coming in the competitive examinations. They are tricky problems. The population of a city is 50,000 with a per capita consumption of 130 LPCD. Design the sizing of RSF for the city. Assume suitable data. So forgetting about the maximum demand, average demand. So we'll talk with only average demand here. Average demand is 130 LPCD and the population is 50,000. So 50,000 into 130 comes out to be 6.5, 6.5 into 6.5 into 10 to the power of 6 liters per day. So here this is a rapid sand filter. So 3,000 to 6,000 liter per hour per meter square is the filtration rate. If I assume here 5,000 liters per hour per meter square, Then I'm calculating area is equal to discharge by FR. So accordingly, what I'm getting is a 54 meter square I'm getting. But the maximum limit is only 50 meter square. So what we have to do, we are divided into two. Two beds are to be provided. The area of each bed will be equal to 27 meter square. The L by B range also we know 1.25 to 1.35. If I assume 1.25, then what I'm getting here correspondingly B is equal to 4.7 and L is equal to 6 meters. So two numbers of 6 meters length and 4.7 meter width bed you have to provide, and if required you need to provide something as a standby. So normally what will happen, why standbys are required, if you look at this, water will be flowing through central channel like this. So this is central channel. Now this will be the bed number 1, bed number 2, like this. Operation is always a parallel operation. Bed number 3, bed number 4. So the operation point of view, it will go like this. Something like this. So this is the direction of water flowing. So it will be allowed into 1, it will be allowed into 2, and if some problem is there, this line is blocked, this line is blocked and is allowed into 4. So that at any given time, any two beds are under operation and this under repair. So it can be put under repair or cleaning operations. So like this, the operation will be continuous. That's the reason why always we keep parallel beds in operation, preferable, so that some standby also will be there. If only one bed is there, we have to keep one more one as a standby, 1 plus 1. If two beds are there, we have to keep 2 plus 2 as a standby, so that the filter process is continuous and not stopped.